Good afternoon. Welcome to Krishna's classroom. We continue with our discussions on complex measures. And recall that we proved that these are bounded measures. I mean, this is quite a significant difference from the real measures. Now we have seen that the usual non-negative measure that we talk about, light Lebesgue measure, it could be infinite. For instance, on the real line, you see that if you take the real line as x and with the Lebesgue measure, Lebesgue measurable sets and the Lebesgue measure, then you see that the Lebesgue measure of R is infinity. Now, the complex measure is quite unlike the real measures in the sense that they are inherently bounded measures. Now, this is one of the properties that we have already proved by proving that the what you call the total variation of the complex measure mu over x is finite. So that is where we concluded last time. So we had proved this, that if x m is a measurable space and mu is a complex measure, the total variation of mu over x is finite. Now this is something that we can easily establish. Now using this, one can immediately see that all complex measures are bounded measures. So not every real measure is a complex measure. That's important. Because there could be real measures for which its total variation over the whole set may be, for example, the Lebesgue measure over or the Lebesgue measure over R. So they all have this particular property. Okay. So now what we want to look at is possibly the whole class of measures, the whole class of complex measures that you can define over a measurable space itself. So now we can have a vector space structure for these class of measures. Now we will define the following. If lambda and mu are xm, where m is a sigma algebra. Then we define the sum of the sum lambda plus mu and the scalar multiple c mu complex number as follows. And you can easily show that this defines a complex measure. So also so this is the scalar multiple. Now this possibility, I mean, this is quite easy to prove. So I am not going to the details of the proof, but you take it as an exercise. Okay, this is the definition, and using this definition and the property that lambda and mu are complex measures, primarily what you have to prove is this is countably additive, and of course then this property is obvious. That's very simple. Okay. Similarly, of course, if lambda is countably additive, then C lambda as defined here is also countable. And then this is relatively easy to prove, and this is also quite easy to prove. Okay. So that's about the proof. Now, lambda plus mu are complex measures. The collection of all complex measures is a vector space. This is also easy to prove. All the vector space properties can be easily verified, and one can show that the zero measure is the one which attributes zero value to every E on M. Okay, that is a zero measure. And if mu is a complex measure, minus mu is also a complex measure. Okay, and mu plus minus mu is equal to 0. So that is there. Then of course, what is called the associativity, commutativity, existence of a of a additive uh, identity, and then for existence of a additive inverse for every mu is obvious. Then the usual rules of interaction of, of scalar multiplication with addition can be easily verified. That means C times lambda plus mu is equal to C lambda plus C mu. C of lambda mu or C of lambda mu is actually C lambda C1 C2 mu equal to C1 this is the property, that is how the scalar multiplication interacts with the measure. And then of course you have I have said C of lambda plus mu equal to C lambda plus C mu. All these properties are all one can prove. So this is one can verify the entire all the structures of all the requirements of this class to be a vector space. That's easy to prove. Certainly I was a bit confusing you probably by telling lambda mu. Lambda mu does not make any sense. Okay, so that's not right. Right, and that's not required also in the vector space structure. Okay, so all the properties of the vector space can be satisfied. So that's simple. Further, we can introduce a norm on this. Introduce a norm on this as follows. Okay, for every mu first of all, this is well defined. Now you have to show that all the requirements for this to be a norm are satisfied. And what are the requirements that you need? Need this property. Zero. Then equal to 0. 2. Here you need some work, but that's straightforward. And then the third property is now this is quite easy to prove here. Now these are quite easy. Therefore, this defines a norm on the class of all complex measures on script. So if you want, you can designate this by this. Vector space of all measures over there. Although this is not a standard notation, I have just introduced. Okay, so then what we have is this. Then all this. Now we talk about what are called and now you see that if mu, see we can identify this is the properties of a real value or a real value function. Okay. So let it's a real value such a measure is because here we are assuming a real measure. A real measure, here we do not assume that is a positive measure. So it's not the usual classical measures that we are talking about, but a real valued function. Okay. Now, define the total variation of the real measure is exactly like the following. Suppose you have got a collection En of measurable sets which are disjoint. Okay. Then you work out this one. En class of functions. You compute this. En. So you have E and En is a partition. The partition on E means what? It's a collection of disjoint sets such that mu E so this property is satisfied. So partition. Now what do you take? So you take this one, sigma mod mu En for every such partition. Take the supremum of this. If you take the supremum of this, that supremum will be what you obtain as mod mu of x. Okay. It's the same way in which we have defined for the general complex measure. It's just the same value. The only difference is that now you are talking about a real measure, which you call a signed measure. So we are not insisting that it's a non-negative measure, but it could be both positive and negative. Just like telling a function which is not necessarily not necessarily non-negative. So we will, in fact, there is a connection between such functions and these kind of measures that we will look at later. But then now you define mu plus to be and mu minus minus b. Now you can see that both mu plus and mu minus are non-negative. Then both Now the analogy is this. Suppose you take a function, take a, a function which takes positive and negative values. Okay, so f is a real valued function. F is a real valued function on R. Okay, now to define following. So define mod mu to be equal to mu wherever mu is positive is equal to minus mu x is negative. Okay, and equal to 0 where mu is 0. Equal to 0. 0. Okay, now define. Now in this case, you have a positive real valued function. Oh, okay. So you see, it looks like this. So this is the function that you end up with. Okay? You have this one. Suppose this is your sorry, right, f here. F. Okay. Wherever it is positive, you take it. You take this as the reflection of this, and then you have this one, and then you have. So this is what you call mod f. Okay, right? Now suppose you take this one. So you look at this function and then define mod f plus f. Okay. So you will end up getting the places where this function is positive. Otherwise, wherever the function takes, the original function takes negative values, there the function is going to be 0. So you will end up with this function. I just mark it out. So you are going to get this as f. This is your f plus. Similarly, you write minus. So what happens is wherever it is originally positive, then it is going to be negative. So it's going to be this one. This is there. So this green one is what you call this. So you get F plus and F minus as I mark. So this is similar to this. Okay. A similar definition that you work. This is what you are familiar with, and therefore in the same way for mu as in, okay. Now then you observe that mu is essentially equal to plus and mod mu so this is there are similar results available for that. Okay, so you get F is equal to minus and F so this is what you end up with. Okay. So similar to that, you have this property which you designate by mu plus are called positive and negative perspective. Now, this is called mu as is called the Jordan decomposition of remember that both mu plus and mu minus are positive negative variations respectively. Okay. So both mu and mu plus and mu minus are essentially the non-negative measures. Okay. So it's from there that we compute this one. Right. This is what is called the Jordan decomposition. What next? Now remember the representation of the measure as the difference of two positive measures as the difference of two positive measures is not unique. But the Jordan decomposition has a certain minimal property. For instance, if you take F, you take C positive, you take F plus C, you take, so write F plus G equal to G. Okay. Then you can write F plus as half of mod G plus G, like this. G minus. So this you can write F as, okay, so you have, sorry, you can write this as G plus and G minus. Then you see that your F minus is essentially that's another representation. So from among all the possible representations of this, of these functions, or for that matter, these measures, similarly analogous to that, you have the representations to see that this, what you have defined here, has some minimal property, and this is something special about this. Now we shall consider this later in detail. Just remember this at this moment. Now let us work out a few properties of this measures. We make some definitions, and in the process of comparing measures. Absolutely. What is sigma algebra? Let lambda be an arbitrary vector that means a complex measure on M. Lambda may be positive or complex, whereas mu is a real positive, whereas lambda may be positive. We make some remarks. A complex measure because it's a map from, see, if lambda is a complex measure, lambda is a map from into C. Okay. So its domain is M and the range is this. But a positive in its range a point that on our example, that is the example. Okay. Thus, a positive measure need not be a complex measure. Why it cannot be a complex measure? Because a complex measure has the property that the variation, the total variation, see if mu is a complex measure, then finite. Whereas mu is a positive measure, then mu of x may be equal to infinity. This is possible. Okay. So this is the difference between the for a complex measure, the total variation of mu on x is finite, whereas mu x may be equal to infinity for a real non-negative. So that's just a remark. Now we introduce some properties like some terminology that we want to make use of. Okay, so I think this is the right place for us to stop. Since I started late, maybe I would discontinue here. And next time I will introduce the concept of what is called absolute continuity, measure concentrated on a set A, and then measures which are mutually singular. So these are the three concepts that I am going to introduce, and then also work out the consequence of such definitions. Okay, thank you very much.